All right, Chapter 7, Section 2, Properties of Parallelograms. Okay, we're in this unit of quadrilaterals and other polygons. That was the name of the unit. For the record, we are done with the other polygons aspect of it. That was really only in the opening section where we were talking about some of the properties of angles and how it, on a macro scale, extrapolates out to larger and larger polynomials, or at least more sides. And starting in this section, for the next couple of sections, we're going to talk about a particular set of quadrilaterals, which will be the main focus for the remainder of the unit. Okay, but the particular set of quadrilaterals we're going to talk about for the next couple of sections are parallelograms. Parallelograms. Now, it's in the name itself, but the term parallel is one that you will have been familiar with for a couple of years now, dating back probably until middle school. But we can approach this in a few different ways. First off, I want to kind of get us used to the terminology, the notation rather in these diagrams. You'll notice these little red arrows as part of our pictures. These imply parallel. And the reason why we have double red arrows versus single red arrows is, for instance, these single red arrows are parallel to each other, but not parallel to these two, which are parallel to one another. Okay, so the way we would write that using geometric notation, off here to the side, you see there's our segment notation. Segment AB is parallel to segment CD. There's the symbol for parallel, those two side slash marks. Segment AD is parallel to segment BC. So there's AD and BC. Those two will be parallel to one another. Okay, so the formal definition of a parallelogram is it's a quadrilateral, a four-sided figure with two pairs of parallel sides. As we just noticed here, AD is parallel to BC, and then AB is parallel to CD. Okay, two pairs of parallel sides. Now, just to remind us about what the term parallel actually means in the mathematical universe, a couple different ways to think about it. First off, from the kind of a visual or physical perspective, if I were to imagine this line segment instead of being stretched out into infinity, continuing on forever beyond this shape, as well as this segment BC, the same thing happening there. If I were to extend both those lines off into infinity, they would never cross each other. They would never touch. They would never intersect. Okay? They would never touch each other. They would never get any closer together. They would never drift any further apart. Okay? That is by definition parallel. Okay? The other way we can look at it would be on a coordinate grid, which is convenient considering this is on graph paper. And that would be that it had this been in a coordinate grid realm, we would talk about slope. And this is probably the way that you're probably more familiar with it because it's easier to measure and visually see and stuff is on a coordinate grid. But we can kind of see here just on my graph paper from D to A, it is a rise over run or a slope of up 3 over 2. So this would have a 3/2 slope right here. And then we can see that we have the same exact slope here from C to B, up 3 over 2. So a 3/2 slope there. And because of that matched slope, that means that as I go from point to point along that line, that those lines will never get any closer, never get any further apart, and therefore be parallel because they'll never intersect in the coordinate universe. And we can see the same thing here with A, B, and CD. Both of these would have slopes of 0, so they'll never get any closer or any farther apart. But that was just to remind you what parallel means. So in terms of the actual geometric shape itself, this quadrilateral, this four-sided figure, a parallelogram means that it has two pairs of parallel lines, or parallel line segments rather. Okay. So in this section, we're going to focus on the properties of parallelograms. And what do I mean by properties? I'm talking about things that are true of any and all parallelograms. Okay, and this is, again, where I'll reference the fact that geometry is very abstract, even though it's very easy to just latch on to this visualization, the specific shape right here. This is a representative of any and all parallelograms. If it helps, over here in the margin, you could throw in a couple examples of very familiar parallelograms that you'll already know about. That would be the shape of a square. A square is a parallelogram. A rectangle, also a parallelogram. And a rhombus, which is essentially a square if you kicked in one of the corners and bent it sideways so it was diagonal. A rhombus is also a parallelogram. Those are just a few that you're probably already familiar with, but they are also going to follow these properties. All right, so let's talk about the first two major theorems. Okay. Here are the first two major theorems regarding any and all parallelograms. So not just the one you see on the paper, but anything else that is also a parallelogram. First off, parallelogram opposite sides theorem. Now, one thing I want to point out here, I'm never going to expect you to know the name of each of these theorems. There are literally thousands of theorems in the mathematical world, and I am not going to care if you remember the names of them or not, but I will care if you know what they do, or at least being able to associate them with the correct shapes and that sort of thing. So, for instance here, I don't care if you know the name of it, but what I do care about that you know is that for any and all parallelograms, like we see here at the top, opposite sides will have to be congruent to each other. Opposite sides will have to be congruent to each other. So here's where we see another geometric term here, congruent. Congruent literally means that they match, they are the same. And we can use that, we'll use that in an example in just a second to create an equation that if two things are congruent, then their measurements must match. They must be equal to one another. Okay, so for instance, in this top quadrilateral, this top parallelogram at the beginning of our notes, segment AB, whatever that would measure, whether it's on a small scale like millimeters or centimeters, or if it's on a really big scale like miles or something like that, from A to B has to be the same exact distance from D to C. Same thing goes for D to A. That has to be the same distance from C to B. And that's important because if the opposite sides of a quadrilateral are not congruent, that means it cannot possibly be a parallelogram. Okay, so it goes both ways. It's kind of like flip sides of the same coin. Whether you begin with a shape like this, and this is the shape that, and by shape, I mean like this is the type of diagram you'll see most often in this section, where you begin with the fact that you're dealing with a parallelogram with these red arrows. If you start with the parallelogram, that implies that opposite sides are congruent. But also, the flip side of the same coin, I could start with this diagram right here, that if I have a four-sided figure in which opposite sides of that quadrilateral are congruent to one another, that also means that that shape must also be a parallelogram, meaning that if I start with a four-sided quadrilateral with opposite sides that are congruent to one another, opposite sides must also be parallel to one another. Okay, so they go hand in hand. Similarly, we get the second theorem right here dealing with opposite angles. So not only will opposite sides have to have the same side length, but opposite angles or diagonal angles will also have to have the same measurement in degrees in that case. Again, using that term congruent. So for instance, again, using our larger example up here at the top of our notes, that would mean that angle A, whatever degree measurement there was right here for angle A, would have to match and be the exact same as angle C down here. It's opposite angle going diagonal across the parallelogram. And similarly, angle D right here, a little more acute in this case, whatever measurement was right here would have to match angle B up over here, diagonal to it. Okay, and just like the last theorem, it goes both ways. So if I started with some quadrilateral like this and opposite angles were congruent to each other, given by these little congruence arches right there, that would mean that that shape also has to be a parallelogram, so that opposite sides would be parallel to one another. And then also, that would mean that opposite sides would also be congruent to each other. So all three of these go hand in hand. Okay, so how will you see this in an assignment form? How will you see this when you're asked questions about it? And so let me scroll down a little bit here so we can see a couple of examples. I'll do one of these examples for today's recording because they're both very similar. Okay, but this is essentially what you will see in your assignment. Okay, you'll notice that in both these diagrams, you see these red arrows again. Okay, again, those red arrows for us in the diagram will mean that those sides are parallel to one another. For instance, the single red arrows are parallel to one another, and the double red arrows are parallel to one another. Okay, so you'll start with that kind of information. And then it'll get a little bit busier because I'll give you some other information regarding length of a given line segment or side, and then angle measurements. Okay, so let me jump to the whiteboard and I'll show you how we're going to go about solving that using these two theorems that we just covered. Opposite sides being congruent and opposite angles being congruent. All right, so I'm going to do example B from that. So this is the shape that we are going to start with. Okay, so this is a quadrilateral. It is a four-sided figure, but also in this section and in the next couple sections, we're going to be dealing with these kinds of symbols, namely these arrow marks. So again, what do these arrow marks mean? That means that the respective line segments or lines that they are on are parallel to each other. They will never intersect, even if I were to expand them beyond just the limits of this shape. And as I've written it right now, where I haven't written arrows on either of these guys, even if they looked parallel, I could not assume it unless it was written. Okay. Now for the record, in the example, the red arrows are there. So that is important. I can't assume something unless it's explicitly given to me or I can prove it mathematically. That's an important aspect of science and math. Okay. But we were given this fact that those double red arrows are there. And it's important to use the two red arrows as opposed to one to show that they're not parallel to all of each other. And that's obvious in this case, but it is important to distinguish that. Okay, so we start with this parallelogram. We know it's a parallelogram because of these red arrows. Now we're also given some other information. Namely, we're given stuff like this, that this segment up here is 3y minus 1. Sorry, I got cut off a little bit. There we go. This line segment down here is 20. This angle up in here is 54 degrees. This one down here is 2x degrees. Okay, a couple things to point out here because, again, these diagrams can get pretty busy pretty quickly. All right. Now, there are, again, two different kind of major forms of measurement that we're going to be dealing with these sorts of geometric diagrams. The first of which being the length of a segment, right? In this case, this segment up top here is 3y minus 1 units long. This segment down here at the bottom is 20 units long, whatever those units may be. The second form of measurement we're going to talk about are angle measurements, kind of like what we focused on in section 1. And those will be distinguishable by this little degree symbol up there. And the reason I bring this up is because, again, these diagrams can get busy and it may get confusing about like this 3y minus 1. Maybe you thought it was an angle, or maybe you thought like one of these angles was a line segment. Again, the way you can distinguish between angle measurement and length of segment is you'll notice that there are no degree symbols up here in these guys. So length of segment, we don't bother with degrees. Whereas an angle measure will definitely have this degree symbol there, right? Okay, so what we're going to be using here are the two different theorems that we just talked about. The fact that we're given a parallelogram, given by these red arrows, means that I can apply those two theorems that we had before. Namely, the first one was that opposite segments or opposite sides of a parallelogram have to be what is called congruent. Now, congruence, again, means that the two things, the two objects have to match. In an equivalency, or in an equation form, that means that the lengths, the measurement of that object has to equal the measurement of the other. In other words, I can make an equation here. This line segment up top has to have the same measurement as the line segment on the bottom, meaning I can write the equation 3y minus 1 has to equal the 20 on the bottom. These two have to equal each other. Not a terribly difficult equation to go about solving. My job in this equation is to solve for y. So my job here is to get y by itself. I would do that using my regular inverse operations. I would add 1 to both sides so that 3y equals 21. Then I would divide both sides by 3 to find out that y is in fact 7. So again, like I mentioned in section 1, the computation here is not terribly difficult. That was just a 2-step algebra problem right there. But essentially, again, that stemmed from the fact that because of that theorem, that opposite sides of a parallelogram are congruent. That's why this is true. All right, well, what about solving for x? In this case, I'm going to use the second of those 2 theorems, namely that opposite angles also have to be congruent. In other words, these 2 opposite angles have to match each other. I would write that as an equation being that 54 degrees has to match or equal that 2x degrees. And again, I'm solving for the variable here. I'm asked to solve for the x and the y. So in order to do that, I would divide both sides by 2, and I would find out that x is in fact 27 degrees. That one was a 1-step algebra problem, but that's how you'll go about solving it. So you're going to come across those 2 theorems in general, opposite sides being congruent or opposite sides having to equal one another, and opposite angles or diagonal angles having to equal each other or match. Okay, let's move on. Not terribly difficult or strenuous mathematics going on right there, but I have 2 more theorems to talk about before we call it for today's video. Okay, these 2 right here. The first of which is called the consecutive angles theorem. Second, which is the diagonals theorem. These again will apply only to parallelograms. So in this case, this first one, let me just kind of break down the name here. The term consecutive is one you have likely heard before. If you don't know what it means, consecutive literally means in a row or next to each other. So for instance, if I said pick 3 consecutive numbers, 5, 6, and 7 would be consecutive numbers. Okay. So the term consecutive means next to one another or in a row. This is the symbol for angle, that little wedge symbol. So consecutive angles theorem. So when I'm say consecutive angles, I'm talking about angles that are next to each other or in a row. Okay. So for instance, this top left corner angle right here would be consecutive with this top right corner up here. Okay. These 2 angles are consecutive, or this top left corner is also consecutive or next to this lower left corner. Okay. It's consecutive with 2 different things. All right. So what about consecutive angles? Well, consecutive angles are going to be what are called supplementary. Here's another one of those geometric terms that you've likely come across for a few years now. But just to remind you, in case you need it in your margins, supplementary means that these add up to create 180 degrees. They add up to make 180 degrees. Consecutive angles will add up to make 180. So for instance, this top left corner and this top right corner will have to add together, whatever their measurements are, in some way, shape, or form to create 180 degrees. The top left corner and the top left corner and the bottom left corner would also, because they're consecutive angles, have to create 180 degrees. This actually comes from 2 separate theorems. The first of which is one that we talked about in section 1, that in quadrilaterals and 4-sided figures, their interior angle sum, all of the inside angles added together, has to equal 360 degrees. And that's paired with the property we learned up here that opposite angles in a parallelogram have to be congruent to each other. Because of those 2 things paired together, that's what results in this, that the ones that are not diagonal or opposite one another, the consecutive ones, have to be added to make 180 degrees, or also what we call supplementary. The last theorem we'll cover in this section is called the diagonals theorem. If I were to connect each of the opposite corners with one another, I would create what's called a diagonal. And every 4-sided figure has 2 diagonals. In a parallelogram, specifically, the diagonals will bisect each other. There's another geometric term right there, bisect. So again, if you need to write over to the side what that means, to bisect something literally means to chop something in half. So when the diagonals bisect one another, it literally means that it is cutting both of them in half. And we can see that with these little dash marks here. Okay, this little double dash right here and the double dash right here means that both these little halves of that diagonal are congruent to one another, meaning that this other diagonal has cut it directly in half. And the same thing goes for the shorter of the 2 diagonals. So diagonals will bisect each other, only in a parallelogram. Okay, before I end today's recording, one thing I wanted to do is I just wanted to quickly show you guys what we call a negation of what we talked about. So I'm going to show you a different quadrilateral, one that is not a parallelogram, and I'll walk through those 4 theorems really quickly just to show you why it doesn't work for something that's not a parallelogram. So the shape I'm going to draw is one that is probably already familiar to you. This is what we call a trapezoid, one that we'll talk about a little bit later in this chapter. But this is still a 4-sided figure. It falls under the family of a quadrilateral. But this is definitely not a parallelogram, okay? Even if these 2 segments here were parallel, and it doesn't look like they actually are, but if they were, these 2 segments right here are definitely not, okay? And here's how I know. This segment, if I were to continue it on for forever, would definitely intersect with this segment somewhere up here, okay? Because this guy's obviously going to the side. So these 2 segments right here are definitely not parallel to one another. Okay, and because they're not parallel to one another, this is definitely not a parallelogram. It's still a quadrilateral, it's still a 4-sided figure, it's just not a parallelogram, which also means the 4 theorems that we talked about today will not work for this shape. Okay, so let's just walk through them really quickly. The first of the 4 theorems we talked about today was that opposite sides of a parallelogram have to be congruent to one another or have the same length of measurement. It's quite obvious that this top side right here is much shorter than this one right here. So automatically that first theorem is unproven right there in that first step, right? Because this side length here is shorter than that one, that just means that these 2 sides are not congruent. It's still a quadrilateral. It just means it cannot be a parallelogram. Okay. Theorem number 2, opposite angles have to be congruent with one another. Well, let's look at this diagonal right here, the opposite angles or diagonal angles right here. This one right here looks a little bit like it's a right angle. It might not be. It probably isn't, but it looks like it's going to be awfully close to 90 degrees right here. But also quite obviously, this one over here is much, much less than 90 degrees. It's very acute, meaning that these 2 angles will definitely not match each other. They're opposite angles. Therefore, it cannot be a parallelogram. Okay. Theorem number 3 was the consecutive angles theorem that said that consecutive or in a row angles next to each other angles have to add up to make 180 degrees. Now, without any specific measurements here, I can't confirm or deny it, but one thing that we see here is that this one looks an awfully lot like 90 degrees. The only way that this angle right here would be supplementary would be also if it was about 90 degrees, and it's quite obviously much more obtuse. So that's disproven right there between those 2. Even though these 2 right here look like they might be supplementary of each other, they might both be 90 degrees or at least awfully close. We can see that not all consecutive angles do that same thing. So this is definitely not a parallelogram. And finally, theorem number 4 had to do with the diagonals. If I just quickly draw the diagonals in this figure, connecting the opposite corners, that was a really bad one. Connecting the opposite corners here. Okay, it's a little less obvious with this diagonal right here. We can tell that this piece up here on the top is a little bit shorter than this one right here, but where we really see it is with this longer one. This piece right here is definitely not congruent to or the same length as this longer piece right here, meaning that this longer diagonal is not bisected, meaning that this cannot be a parallelogram. Okay, so that's where I wanted to end today's video. Tomorrow for wrapping up section 2, we'll run through a couple of quick examples and see what happens on a coordinate grid for this stuff, but I'll go ahead and stop recording right there.